Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on June 30th, 2025, about 4 days ago. It introduces a new model for radiology that, despite being up to 14 times smaller, consistently outperforms much larger baselines. The paper is titled µ2 Tokenizer, Differentiable Multi-Scale Multi-Modal Tokenizer for Radiology Report Generation. And as we'll see, this approach has significant potential for medical AI. This work tackles the challenge of automatically creating reports from CT scans, proposing a new way to fuse image and text data. Also, the authors shared their work on GitHub, and it's pretty well organized. You'll find the official source code for the model, along with installation instructions and even links to pre-trained model checkpoints on Hugging Face. It gives you a clear path to start experimenting with this yourself. Alright, so let's look at the overall architecture. This first figure gives a great overview of the proposed µ2LLM model, which is designed for the task of radiology report generation, or RRG, that's automatically creating reports from scans. On the left, it takes a 3D CT image and a text question as input. The image is split and processed by an image encoder, a VIT 3D model, while the question is turned into embeddings, which are basically numerical representations. The key innovation is the central µ2 Tokenizer, which cleverly fuses these two streams before feeding everything to an LLM to generate the final report. So, digging deeper into that µ2 Tokenizer, this diagram really unpacks its components. It starts with the visual tokens from the CT scan. These are first enhanced using relative positional encoding, which essentially helps the model understand the 3D spatial relationships between different parts of the scan. Then, the process uses Differentiable Token Selection. This is a soft selection method that intelligently picks out the most important visual features without simply discarding the rest, which is key to preventing information loss. Finally, these refined visual tokens are combined with the text query to produce one powerful, fused embedding for the LLM. Building on that tokenizer, this next figure shows how the model is trained using a clever feedback loop. This process is called Direct Preference Optimization, or DPO, which is a way to fine-tune a model based on which answers are better. First, the µ2LLM generates several possible reports. Then, a special evaluator called the green model scores each report for its clinical accuracy, assigning it a green score. This scoring creates preference pairs, for example, marking one report as a winner and another as a loser. The model is then updated to favor producing reports like the winners. Moving to the this table really shows the payoff. It compares the new µ2LLM against several much larger models on different datasets. We see a few metrics here. Rouge and Meteor are common ways to measure text similarity, while BERT score is a more advanced version. But the key one is the green score, which measures that clinical accuracy we talked about. Across the board, the 1 billion parameter µ2LLM, especially after that direct preference optimization step, dramatically outperforms models that are up to 14 times larger. So to wrap things up, what this work really demonstrates is a powerful two-part solution. First, the µ2 Tokenizer intelligently selects and fuses the most important visual and text features, preventing that critical information loss from the CT scans. Second, using direct preference optimization guided by a clinical accuracy score, it fine-tunes the model to produce genuinely meaningful reports. This approach really opens the door for more efficient and trustworthy medical AI. That's all for today. Thanks for tuning in to the AI Research Roundup.